exam
December 4th.
December 4th.
Okay.
Final exam December 4th. Okay.
I
Yes.
think the first we'll have final exam 1 and final exam 2, right?
No, this is for final exam.
Okay,
Okay, I'm speaking about final exam.
Oh.
Okay, the schedule for final exam here is should be our class between 5 to 8 or 5 to 7.2, between 5 or start at 5. Wednesday here. So Wednesday 4, okay, between 4 and 6.
What
The
did we
exam will be between 4 and 6. So the exam will be at 4 o'clock, not at 5.
Not 5, yeah.
Yes, according to the exam schedule. Why? Because here, Wednesday, your class at 5 o'clock, right?
Yes.
exam?
Today, 5 o'clock at 5. Wednesday, okay, so the day for the exam,
At 4.
Wednesday, December 4th,
4 p.m.
between 4 to 6,
Yeah.
okay? So the exam will be between 4 and 6, okay?
Okay, so
No, between 5 and 7, 4 and 6.
No way.
Now, this is for final exam. I will send you email and I will send you the topics required. The topics required after the midterm exam. The topics required after we took, if you remember, you took one lecture after midterm exam about the design of the solar cell. Okay, some questions and examples. Then we started with the wind turbine. Okay, wind turbine. Today, week number 11 should be number 9, 10, and 11. Okay, today we will continue with the wind turbine, and next week, let me show you this one. Okay, today, November 6th. We have 1, 2, should be 3, but I don't know. Each year, last year and before last year, school give notification before the Thanksgiving Day, Wednesday, early release. So I don't know this year is okay or no,
okay.
but maybe 95% is will be early release, so no class here.
Okay. And Friday.
Okay, no class
No class
here.
on Wednesday.
So we have 1, 2. Today, okay, 6, but 13 and 20. 20 second exam. 20
Second exam?
second exam will be, okay, will be second exam, exam number 2.
Okay.
And final exam December
4th.
4th.
So will it be from 4 to 6? Oh, well, no, my bad.
For
No,
second
that was-
exam, no,
5.
same lecture time.
Okay.
5 to 7, okay,
Okay.
but for final, because according to the rules of the school should be
So is it the same as the other class?
for other class is we said Monday,
It's still the
yeah,
same, all right.
5 at 5 o'clock,
Yeah.
okay, but this one is
4 to 6.
okay. Any comment about this second exam? I will send you email. All details about second exam and third exam. Also, I will send you the schedule for the final exam. Final exam, we say Wednesday, December 4th, between 4 and 6 o'clock, not at 5, at 4 o'clock.
Okay.
The exam will start. And the second exam November 20.
Okay.
Okay, November 20.
This is the third exam. We did the midterm.
No, midterm.
Oh, midterm.
First, we have two
Okay,
exams,
okay.
1 and 2. Exam 1, exam 2. So the second exam is 20. Okay. Today we will discuss the wind turbine design, some examples about the wind turbine design, and we will discuss power flow of the wind turbine. Next week, November 13, review examples. Okay, that's examples. Okay, and 20 will be the second example. Now, you remember last week we stopped at example 16, right? We discussed some examples about the wind turbine, but we stopped at example 16. So today we will continue for example 16, and we will solve some advanced examples and design examples. Okay. Now, for the second exam. For the second exam, questions 4, answer 3. 1 question about the design of solar cell. 1 questions about the design of the wind turbine. 1 questions about the power flow of the wind turbine. Okay, and one question about the wind turbine, not design, just calculate. Okay, so 4 questions, answer 3. 2 of them design solar cell, design wind turbine, and 1 power flow. Power flow we will discuss today. Okay, and 1 question about solar cell. Wind turbine. Calculate, just calculations, no design. So now, example, calculate the wind shear effect given wind speed at 20 meter equal 7 meter per second. This is speed. Okay, meter per second. But this is the height of at 20 meter. This is speed. But at 1 meter, more or high?
Is lower.
Lower.
No,
Okay, lower than. Okay, lower than 7. Okay. The height is 100 meter. Here exponent alpha 0.15. You remember alpha, I think last week we say alpha in table here, and I think this lecture or this lecture. Here alpha 0.1, 0.12, 0.14, depend on the area. Okay, so we say 0.15 select as standard, or given 0.15, or given. If you need it, you can assume 0.14. Okay, this is from last week lecture. So again, here I think is given. Where is this one? Right, this one. Okay, so 0.15 given, 0.15, not 0.14. This one. Okay, the formula used V hub equal V reference times H hub divided by H reference power alpha. So we have the high and we have the H reference because he gave you the speed at 20 meter, but the hub height is 100. So use this formula, power to alpha, to get the velocity at the hub. I mean, techniques again. See here. The speed, the tower 100 meter, okay? The speed at 20 meter, the speed of the wind at this high is 7 meter per second. He wants the speed here, wind speed. Okay, so we can use this formula. V, yes. V, this is V velocity. Yes.
The speed, is it for the
100.
No, what I mean, for the rotation? Is it for the rotation?
The speed of the wind.
Wind, yes.
Yes.
Okay.
No, this wind speed.
Wind speed, okay.
Okay, this
Okay.
is we say this area.
Okay.
Okay, but he wants the wind speed at this point. Okay. Wind speed in Houston should be more than 12 meters per second. This is the standard, okay, to rotate the place. Okay. So, it's a very easy example. Example 17, calculate the operational load cycle. Calculate the operational load cycle. Operational hours per year, 5,000, and cycle duration 2 hours. Load cycle is operational hours divided by cycle duration or cycle period. Cycle period 2 hours, he said, okay, 2 hours. Cycle duration 2 hours, so means 5,000 divided by 2 equal load cycle 2,500 cycle per year. Okay? Any question? Load cycle. Calculate swept area. He said radius 75 meter. So swept area equal pi radius square. Okay? Why? Because here, this is blade. 75, this radius 75 meter, okay? Radius. If I give you diameter divided by 2, okay? So this is radius. So the area equal, according to this formula, pi r square. Pi r square is the area of the circle, okay? Pi times 75 square equal meter square. calculate dynamic load. This is very important, dynamic load. See, calculate dynamic load on the turbine. If the given data, mass of the blade, 15,000 kilogram, wind speed 12 meter per second, and drag coefficient or constant coefficient 0.9. Now, use this formula, F force, okay, 0.5 half CDA rho V square, CDA rho V square, okay. So for this examples, we have this one, 0.9. Wind speed is V square. And mass of the blade, if you remember last week, these equations, I think it's first by this one. Okay. Area, area, and this one, this is the sheet of the formula sheet. This one. Okay. Covered by this example, similar to this example, rho optimal rocker diameter, calculate. This one. Same this one and this one. Torque and inertia, and determine this one. Okay. So 3 questions in 1 question. Try to solve this one as homework. I will show you where is this. Same this. Same.
So,
Calculate the load distribution of the same this example. Okay. Just this formula given. Okay. CD given here assumed, but the question given. Okay. Rho you can, if given, okay. If no, you can assume it 1.225. This is standard. Okay. A, if given the speed, given the blade diameter or radius, you can calculate it to calculate the force. Okay, I will show you the question required. That is five. Question number 90. It's held just assume an effective area and calculate this based on the drag impact. CD given here 0.9. Not given, you can assume it 1. Area or rho. Rho not given, you can assume the area, you can assume rho 1.225. Okay, you can assume. Next examples, we will solve this problem, okay? Same, this one is, you can solve it for, as assignment. Assignment 6 and assignment 7.
So, what's the change, what's the difference?
This is power output. Power output.
For what?
It's power output. It's no power. It's force. No force. This is power output given. And here temperature 25 and heat dissipation factor 0.8. Okay, try to solve it if you can. Okay, if no, I will solve it next week. But this example is very important. Okay, for the final and second exam. Yes.
Don't we need the radius or diameter for?
Yes, you can assume 75 or 70 because this is
Oh.
design.
Oh.
Design, you can assume. Okay,
Okay.
you can assume.
So, example 7 and that
Example 19 and 20. Try to solve it, then and submit through the system as assignment 6 and 7. I will open assignment 6 and 7. Try it. If no, next week, because next week just examples and review. Next week, examples and review, I will solve them. No. So, due date for these assignments next Wednesday before the class. To submit it, yeah, next Wednesday before the class.
Alright.
Why? Because I will solve it in the class,
Okay.
okay?
So,
please-
we solve and upload?
Yes, submit and upload to the system for the class, before next class, next week class, okay? Now, design examples. Example 1. See, this is design. Example or assignment 6 and 7 or example 19 and 20, previous examples. This design also. This design. Okay, so we will solve here some examples about the design, how to design wind turbine. Example 1, calculating about the calculating of the optimal blade length. Optimal length or optimal radius. Optimal radius of optimal radius. And at maximum efficiency. Okay. Data given, average wind speed 10 meters per second, desired output power 500 kilowatts. We have a lot of power rating for the wind turbine. We have 2000 kilowatts. We have 4000 kilowatts, 7 kilowatt, 1000 kilowatt, and we have 500 kilowatt. So this desired power. If you want to design, maybe I will ask you to design wind turbine and no mention to the power output. You can assume it as 2000 kilowatts, 2000 kilowatt or 3000 kilowatt. For
design outputs, for,
sorry,
can assume for design power outputs, 2000
2000 kilowatt
kilowatts.
for design Yes, small size, or 3,000 kilowatt, small size, okay? Wind turbine. Now, here given desired output power 500 kilowatt. Air density, see here is 1.225. Air density is constant. This number is constant.
Thank you.
Okay? So, memorize this. This is very important. You can assume direct 1.225 kilogram per cubic meter. Power coefficient CP, we have two functions now, CP and CT. CP, power coefficient CP, 0.4. 0.4. He say design. So design, we have this formula. We have P, we have CP, and we have rho. We have velocity or no? Velocity, average wind speed, 10, we have. So we can calculate A.
Why us?
We can calculate A. Area of this circle area. From area we can calculate R. R from area,
Yeah, we
okay,
can find
you
out.
can see it. Okay, from area we can calculate R. Okay, R squared, then take square root for both sides to get R. R is the length of the length. That's it. Okay, we design the plate. It's designed for wind turbine. Okay, but maybe in the design I will give you one table requirement. Length of blade, and another section is maybe I will the second A calculate length of a blade. B, if the length of a blade, I will give you another number. Calculate the P generated. Okay. Now, the optimum plate equals 16.1 meter. Now, calculate the tower height. This. Depend on the given data. Here, speed at 10 meter, 5 meter per second. So, he says the speed at 10 meter. This 10 meter. The speed is 5 meter per second. Okay? Per second. Okay. This is V naught or V reference. Reference velocity. This is velocity, not voltage. Now, power law exponent alpha 0.14. We say for the design, if you need it, you can assume 0.14. Okay? why? Because this is depend on the location of the installation of the wind turbine. Okay, so in a free space, 0.14, and in land, free is no building, no any thing is 0.14. Okay, you can assume 0.14. Alpha 0.14. So he gave you the high H naught equal 10 meter, V 5 meter per second. So we can use this formula, V equal V naught H divided by, this is not this H naught, okay, but H naught here 10, okay, 10, so I put it 10 here, power alpha. Okay, if we need, he said, select the operator tower height based on the wind profile. Okay, determine the height maximum. Okay, this one. We can assume H 100 to calculate the velocity at 100, or we can write a program. Okay, we can write a program to give the speed related to speed at any meter or at any centimeter or any feet, any 10 feet or at half the or middle of the tower. Okay, we can write another program to calculate the velocity or high or any unknown values as alpha. Now, to calculate material selection for turbine blades. Now, these questions, I will give you these questions or these examples with the other example. I will combine example 3 and 1 or 3 and 2. Okay, so now should be when you study for this for next exam should be create examples to combine example 1 and 2 or example 1 and 3, example 1 and 5 or 2 and 3. Okay, combine 2 or 3 examples together to design wind turbine. Okay, so please next week we will discuss more examples about the design. I will combine 2 or 3 examples in one question. Okay, and I will solve it because second exam and final exam includes one question about the design of the wind turbine. The design is 1, 2, 3, 4, more requirements, okay? And depend on the more standards. Same standard 1.225 row 1.2, you can assume it 1.2. This is standard, okay? You can use it direct. Okay, or velocity, if you need the velocity, standard in Houston, 12 meters per second. You can assume. Okay? You can assume. Next lecture, also we will discuss advanced examples about the design. Now, choose the plate material to withstand environmental conditions, given force, given 10,000 Newton, cross-sectional 8.05 meter square. First step, calculate the stress. Stress equal F divided by A. F divided by A given 200,000 Pascal or Newton per meter square, because the force in Newton and area in meter square or Pascal. Wow. Okay. Now, gearbox design. Gearbox design. Design a gearbox to transmit rotor motion to the generator. Look here. Here is the generator. Okay, the rotation blades here. First, the wind rotate these blades and transmitted the rotation from the blades to the generator, to the turbine, as turbine. Okay, so here we have gearbox, okay? This is the box here, okay? Should be connected to mechanical parts, joined by mechanical parts, okay? This box is gearbox. The speed at rate, high or low? Low, because it's 12 meters per second. But we need high speed at the generator. Why? We need a standard 1800 revolution per minute as standard. But it's impossible. Maybe 1800, or maybe we can get 17 or 1750, or depend. Why? Because the wind is variable in the direction and the pressure and the force. The wind is variable. Okay, so I don't know. Maybe 1900, but we will modify these values to get 1800 revolution per minute using rectifier inverter set. Rectifier inverter set. Okay, we will discuss later. But now, my question about this gear or gearbox. Okay. Rotor speed 15 revolution per minute. Desired generator speed 1500 revolution per minute. Okay. So gear ratio or gearbox ratio is the generator speed to the rotor speed. Generator speed, this is generator speed. Okay, and here the plates. Okay. We want this ratio. This ratio is the speed N generator to N blade. So N generator to N blade equal 1500 divided by 15 equal 100. Okay? This ratio to this one should be more than 1. Means the speed on the generator more than the speed of the blades. Okay? Any question? Any question? No? Do you need this page? No? Okay. So choose the gear force with 100 to 1 ratio or 100 is fine.
You mean the ratio between the radius of two gears?
The generator 100 and the other, the plate is 1.
Is there any condition can the other way around?
Yeah.
Maybe it's the one to be higher than the other one.
Yeah, it's fine. Yeah. The shape is not really. Do you mean this one here?
Yes.
Okay.
Yes.
And here?
Yeah.
One. Okay. So this is radius G and this is radius B. Okay? Because radius G to radius B should be inverse with the speed. Okay.
So
and B to N
G.
G. Why? Because this less than this radius here less than this one. So the speed here more than. Okay? More revolution than. Okay? It's the shape is not this here. Here. Teeth around there. Okay? And here another one. Okay? And the number of teeth, see here, teeth of generator divided by teeth. Yeah. Okay. And omega blade angular velocity divided by omega. Same speed. This is speed revolution per minute. This is radian. This radian. Here, second. And this is revolution. Here,